Okay, so I guess we got started. So first of all, the first thing, as usual, is there any questions about last time? I'll say a few words about what I did last time. What the significance of this was, and I didn't kind of completely get through the material in chapter 3 last time. So I'll say a bit more about the last couple sections of that, which should also kind of give more of an idea of what I was trying to do in that chapter. But are there any other questions about what I did talk about last time?
Professor, I have a question.
Sure.
We constructed the SU2 group last lecture, right? By taking the exponential of the inner product of a vector to the groups to the basis of matrices, sigma 1, sigma 2, sigma 3, right?
Right.
I wonder why we didn't include sigma 0, because any self-adjoint matrices can be represented as a linear combination of these four matrices.
Right.
And these four matrices, I mean, by your definition, should be the generator of this SU2 group, right?
Yeah.
So if I take the exponential, it should automatically generate all SU2 matrices, but we didn't include that sigma 0. And if we did include that sigma 0, it turns out that we don't have SU2 group, we don't have matrices in SU2 group because their determinant may not be 1.
Yeah, exactly. I'll say more about that, but yeah. So that gives the the most general thing. If you exponentiate any of those four matrices, what you get is U2. You get all unitary matrices. So I think I'll say more about this, about the difference between all unitary matrices and the special unitary matrices. But that's the difference. So it turns out that that extra factor, exponentiating the exponentiating I times the identity matrix, that's really just giving you back the U1 case from before. So I was it's true in general, if you exponentiate a general 2x2 self-adjoint matrix, you're going to get a unitary matrix. But I wanted to to put the U1 part of it to the side, because that in some sense we've already talked about, and we want to talk about the new part, the SU2 part. Okay.
Okay, so yeah, you mean those generators actually generate another subgroup of U2, not the SU2 group, right?
No, just the SU2. Yeah. So if you look at those three generators, actually, I'll go over this again, and I wanted to kind of go over this again anyway. But yeah, if you exponentiate, constants times the Pauli matrices, or e to the I times constant times the Pauli matrices, what you get is SU2. And SU2 is a subgroup of U2. It's a subgroup of things with determinant 1. But I'll say more about that. But yeah, it's true. At some point, I didn't really say that very carefully. But at some point, the general problem is really about U2, and I was kind of specializing. I was kind of throwing away the U1 part of it and not talking about that because that's that problem kind of separates into a different. You can kind of pull that factor out and deal with it separately. Okay.
Okay. Thank you, Professor.
Okay. Anything else? Okay. Let me then get. Yeah. Does somebody have some?
Yeah. Sorry. Just as a sanity check, the inner product that we were using to do v dot sigma.
Yeah.
In the previous lecture, that behaves like a regular dot product, right?
Well, actually, it's probably not a good idea to. That's a very confusing thing to think about as an inner product. What I just really meant it to be the notation for V1 sigma 1 plus V2 sigma 2 plus V3 sigma 3, just to avoid writing that. But what you're doing is you're taking the. I mean, if you try to think of it as a dot product, you're taking a dot product of vectors in R3 and 2x2 self-adjoint trace 0 matrices. They're both three-dimensional spaces, and you're taking a dot product between two different kinds of three-dimensional spaces. So it's very confusing to try to think about it as a, you know, what's the geometry of that inner product? It's not really an inner product. It's really just a notation to avoid writing out that stuff.
Okay, so it's just a shorthand.
Yeah. I think it's just going to get confusing if you try to think of it as an inner product, because it really isn't. Any other questions? Okay, so let me get back to then where I was last time, and I was trying to get towards some things that were at the end of the chapter. Let me kind of finally get to that. So last time, maybe it's a good idea. So in some sense, to explain what I'm trying to do, it's a good idea to kind of explain that this is a generalization of what you know about U1. So in the case of, we're going to generalize this. It's the U1 story. And the U1 story that we're trying to generalize is really just that, you know, things in U1 are of the form e to the I theta, but you can expand out the exponential and say that if you're near the identity, these things are approximately 1 plus I theta, right? And then if you expand out this exponential, they're higher order terms, but is for theta small, or, you know, so infinitesimally, this is really what's going on. And if you try and draw the picture, you've got a unit circle, and it's going through the identity here, and this is the identity of your group. But then the tangent space to the circle at this point is this. And but the equation of this line, this line is really the is one. Well, if we take it's 1 plus I times actually maybe it's better to say that this is for this is small. This is 1 plus I epsilon times something small. Well, the equation of 1 plus I epsilon times something small, this equation is just this tangent line. Okay, so this is kind of a trivial fact in 2 dimensions, and this is kind of a trivial fact with this. But we're gonna try it over today, and then next week we're gonna exploit a lot about what happens for a general group. For general group, which is much higher dimensional, of what can you say about the tangent space near the identity, and that's in some sense what we're going to be trying to do in this whole. A lot of our whole technique will be to replace what's going on the whole group, which is complicated, by just understanding what's going on right near the identity. And so we want to generalize that, and so what I did. So for SU2, so I used. I use these anti-commutation relations for the sigma matrices, which is this fact. Now the anti-commutator, so it's that times that plus the opposite direction, and that this was 2 delta jk to show that if you, and this is the confusing thing that you're asking about, that if I took if I took 3 numbers and made a vector out of them, and then kind of used them to make a linear combination of 2 by 2 matrices, and I called it this, but you have to watch out, this space and this space are different. This is really notational. That this thing was vector square times the identity. And so then
this also serves as a tangent vector on the group, right?
Excuse me?
I mean, the V times sigma, this guy serves as a tangent vector on the group, right?
Well, we're not. Okay, so I'm not. I'm not saying anything about that now. So this was just motivation. So now I'm trying to go back to SU2, and I want to actually do this very, very concretely. Okay. So later on when I get to the we'll get to some computations later on, which are the analog of this, but we still have a ways to go to get there. Okay. But the first thing, I guess in some sense, what I was trying to do here is to find, here you had the analog of something that you could exponentiate to get group elements, and I was trying to show that the analog of this I theta here is going to be a linear I times a linear combination of Pauli matrices, and so then you use this relation, and actually if you put an I here, well, maybe this is getting too far afield. I think right now I just want to say some very, very specific computational things. So then what you did, so if v squared, so let's assume that we're working with unit vectors, and we can treat the length of the vector separately in the whole problem. And then this guy this is equal to 1. So if you square it, you get equal to 1. And then what you do with this, you use this to show that e to the I, if you take e to the I v vector dot sigma vector, well, I'm trying to figure out different ways of writing this. E to the I sigma vector dot v vector, and multiply that by theta. That if you then expand this thing out, you get cosine theta times the identity matrix plus I sigma vector v vector times the sine theta. Okay, so you have this formula is very much like your e to the I theta is cosine theta plus I sine theta, except now in some sense, in some sense what's going on here is instead of having a single I, you have kind of a unit. I mean, you can do this. You get the same behavior for v vector, any vector on the unit sphere, the unit two-dimensional sphere, and for v vector, any kind of vector of length 1. You can kind of create. You can start doing almost exactly the same things that you were doing in the U1 case. You have very similar behavior. Okay, and so what I wanted to do, the things that I didn't really say last time so much, is that you can use this to show. Let me go back up here. So this is the equation. Let me just leave this equation. This is the one we're going to do everything with. And so this didn't just give me an analog of e to the I theta, but it also allowed me to I could actually now check that, for instance, that these things are unitary. So this just shows that these are unitary. And so you can check that these are unitary and determinant 1. I won't actually go do the determinant 1 thing, but just to see that they're unitary, and we're going to say a lot more about unitary matrices in general, but these are the condition for being unitary is just remember that you want to take so a matrix is unitary when what I'm calling its adjoint, which is the transpose conjugate is the inverse. Okay, and so watch out. This is a very different kind of condition than self-adjointness. In self-adjointness, you say that a matrix is equal to its adjoint, or equal to, or is equal to its adjoint. Here, it's the not that the matrix is equal to its adjoint, but that the inverse of the matrix is. And so this is a different kind of condition. And but you can now calculate what these V vector theta. If you take the adjoint of this, well, what you can do is you can use the fact that these guys are skew adjoint, so that these guys satisfy I sigma vector V vector adjoint is minus. Okay, and you can check that, and this is because if you take these are self-adjoint matrices, these are real numbers. So when you take the adjoint of this, you just this stays the same, and this picks up a minus sign. Okay, so you get this. So these gadgets that you're that you're exponentiating are not self-adjoint gadgets. They're skew adjoint gadgets. And the anyway, so and we'll see this in general a little bit later. That the one way to characterize these unitary matrices is the things that you can get by exponentiating things that are not self-adjoint but skew adjoint, and that's kind of this extra I, this extra minus factor is kind of the difference between. You know, physicists like to think about self-adjoint things because they've got real eigenvalues, whereas the things that kind of behave nicely under exponentiation are the skew adjoint things. Fine. Okay, so what did I want? So, but if you do this, so now if you exponentiate these things again from this the formula where you expand everything out in powers, if you take the this is going to be. So this is going to be either it's going to be the same thing as if you put the adjoint in here, because if you take the adjoint of a product, it's the product of the adjoints, and so in the formula for the exponential, if you expand it out, it just moves up to here, so it's I sigma vector V vector adjoint. This is real. It's equal to e to the minus I sigma vector theta. But you can see that this guy, you know, this is e to some matrix. This is e to the minus this, and you can say if you multiply these things together, this is going to be the same thing. This is e to the sigma vector theta inverse. Okay, so these are units. So these are unitary. Okay. That's really all I wanted to. What thing I want to do with this, and well, but you can see this in many different ways, because this is just a simple fact about 2x2 matrices. But I wanted to. This is one way to see it. Okay, now what I really maybe the best thing to. Okay, I think what I wanted to do with this formula again was to show that we can actually use this to solve the you can use this to understand how to you can use this as a parameterization of SU2 one parameterization of SU2 elements, but you can also use it to solve the most kind of general quantum mechanics problem where your state space is two-dimensional. So let me do that. Okay, so let's go back to. So remember what. So the most general. Number one. You know, state space is equal to C2 quantum mechanics problem. Well, if your state space is just two-dimensional, then your observables, your quantum observables are just two by two self-adjoint matrices. And I showed, you know, and I showed that these are just the sum of something times the identity matrix plus something times the Pauli matrices, right? And so in particular, the thing which governs the dynamics in quantum mechanics is the Hamiltonian. The Hamiltonian is some two by two self-adjoint matrix. So it's going to be some, well, let me call it H0 times 1 plus H1 times sigma 1. Okay, so this is actually the most general Hamiltonian you can write down. If your state space is just two-dimensional, then you know, and you want to understand what it's going to do as a function of time. Well, what it's going to do is going to be governed by the Hamiltonian, and the Hamiltonian there, you know, is there's only kind of a 4-parameter family of possible Hamiltonians, which are these. But remember that the Schrödinger equation was d dt psi. So now you've got a time-dependent state, and it's I d dt is I won't put it in the h bars. H bar is 1. And this, so this is just a two complex dimensional vector that depends on time, and its rate of change with time is given by multiplication of the vector by that matrix. So the solution is t is equal to, if you take this over here, it's a minus sign, and then the solution is given by exponentiating. It's e to the minus I h t, and then the initial condition. Some constants to tell you where you were. Okay. But now the point is that we so you can find the general solution just anyway, so you can find the general solution just by evaluating this guy. And this guy, again, this H is self-adjoint. You multiply it by an I, you get something that's skew adjoint. And then exponentiating some skew adjoint gives you something unitary. And again, you know, the fact that if H0 were 0, then you would get something in SU2. But if H0 is non-zero, then it's a general unitary matrix. And I won't, all I'll just point out is that you can solve this, you know, so this is, you know, you can find this, using this. And one of the points of this formula is you can turn this problem, if you put this in here, instead of v vector, now you're going to have an h vector, and you have to properly deal with the how this depends upon the length of h vector. But you're going to see if this formula tells you the answer. And I think, let me do this. If you go to let me show you here. Go to the, yeah. So I won't write this out in the notes, but if you go to page 32 of the notes, I write this out just in great detail. And I certainly I don't want to do this here, but the point is that you actually can this formula applied, you know, to calculate this gives you the most general solution to kind of any quantum mechanics problem in 2 dimensions, and the details are on page 32. But it's really just kind of, you know, just writing this out and plugging the Pauli matrices in here and writing it out, and you know, figuring out how to rescale things with the if your vector isn't of length 1. Okay. I'll leave that off, but you can see that that's on page 32 of the notes. Let me stop that. Okay. So that's, let me see. And then so we're gonna, so I'm just gonna kind of leave this here right now, that in some sense we've written down the solution to an arbitrary quantum mechanics problem in 2 dimensions. But I'm not actually gonna say any more about it or work out any details. What's gonna happen is in a week or so, I think maybe the week after next. Yeah, the week after. Well, anyway, in a week or so, we'll come to the we'll come to another interpretation of this whole thing, where there's a physical interpretation about that this is actually what happens when you've got a certain representation of the rotation group. And then once we get to that, then I'll talk more about what these solutions actually look like and what the physics of it is. I mean, for now, if you've seen this before, the other thing to notice is just that the one kind of physical interpretation of this is that this is what happens if you have a spin 1/2 particle and you're just keeping track of its whether it's spin up or spin down, and using these 2 degrees the C2 worth of degrees of freedom that tell you about the spin, and you want to see what happens to it as a function of time. And the simplest kind of physical situation is if you put it in a magnetic field, and then where these are the components of the magnetic field, then this is what's going to happen. But again, let me leave this for a week or so from now. We'll go through this in detail and what the physics of this is. But for right now, it's just kind of anyway. Here, this is just the solution to the most general 2x2 problem. Okay. Are there any questions about this stuff? This is kind of an end of this, and this is maybe an end of the part where I'm trying to be very, very explicit that everything is, we're in 2 dimensions. All of our operators are just 2x2 matrices. All of our vectors are just nice, 2-component vectors, and you can solve any problem. You can solve any problem in this way. Okay. Well, let me then go on to the one last part of the SU2 story, which is also quite concrete, but which also then leads into what we'll do next week with the with Lie algebras. Okay, so the other so another interesting formula that the Pauli matrices satisfy is what happens if you take not the anti-commutator, but the commutator. And so here you get this formula, which is this: it's sigma j, sigma k. Okay, so this is now the commutator. This is this times this minus this times this. Well, it turns out you get, again, you're going to get a linear combination. You get a linear combination of Pauli matrices, and the linear combination is given by there's a 2, and then an I, and then your sum, a sum over L, here's the 1 to 3, over the Pauli matrices, and then the coefficients that you get are given by the symbol, which we'll call epsilon I, or epsilon JKL. And this will appear. Maybe you've seen this before or whatever, but this is the thing which is so it's equal to 0. It's 0 if any 2 are the same for any 2 indices. It's the same. And it's equal to 1 if and otherwise it's plus or minus 1, and I should say, and you have that 1, 2, 3 is plus 1. And, oh, sorry, 1, 2, 3. And then if you take these 3 elements and do a permutation on them, you get the sign of the permutation. So anyway, so sign changes under permutation. So that's, anyway, it's a fun, it's a useful notational gadget for this. But anyway, this is true. Now you can make this thing look a little bit simpler by taking. So let's define. Let's change our normalization of the sigma j. So in some sense, the sigma j's are a nice basis that has a lot of nice properties, and physicists like it because it's self-adjoint. But what you'd actually like to do, it turns out for our purposes, you'd sometimes want to work with a basis which is with a basis which is skew adjoint. So let's take xj and write it to be well, sigma j. But we're gonna change normalization of the sigma j's, and what we want to do is we want to multiply it by a plus or minus I in order to make it skew adjoint. And it turns out the choice which makes the formulas work is minus I. Okay, and then it turns out because of this funny to get rid of this funny 2 here, we'll also make this divided by 2. So this I'm just changing these matrices and changing their normalization by a factor of 2 and multiplying them by minus I and making them skew adjoint matrices instead of self-adjoint matrices. Now, if you look at what the reason for doing this is that then the commutator formula becomes simpler. 3 epsilon j k l sigma l. Okay, so we get rid of this factor of 2 in the I here, and we just get this. And so we're going to see a lot more formulas like this starting next week when we talk about Lie algebras. In Lie algebras, a fundamental thing is going to be that you've got a space and you've got a certain basis of the space, and commutators of elements in that space have some nice. Oh, sorry. Obey some formula like this: that if you take a commutator of 2 of them, you get a linear combination of the other one. But this is going to be what you do. What happens for the Lie algebra of SU2? We're going to see general Lie algebras next week. But maybe just another thing to point out about this. Okay, another thing to point out about this formula is that if you if you work with general 2 by 2 skew adjoint things, think of this as a basis, and so let's write A. And again, we're getting back to this kind of confusing notation of thinking of turning these into vectors, but it's kind of but if you write this as that the sum j is equal to 1 to 3 aj xj, and then b vector So if you just have some numbers, so you have some general linear combination of these, and you think of those coefficients as a vector, if you like, or you think of these as kind of basis elements, then the formula, this formula, if you plug in A and B, what you find is A vector, B vector is equal to something which I'll call A vector cross B vector. But what this really means that this is the sum j equal 1 to 3 of A vector, B vector, take the jth component and multiply by xj. Okay. So this epsilon symbol can be kind of, you can do computations with it. It's a fine thing to work with. And if you saw it before, one place you might have seen it was in the definition of the cross product, of the vector cross product. Well, that's kind of because it almost by definition, these are what happens if you take the cross product of epsilon j and epsilon of the jth, take the cross product of the jth unit vector, the kth unit vector, and write it out in terms of the other unit vectors. It's given by this guy. The bottom line here is just kind of that there really is a, in this special case of SU2, this commutator that you've seen here has, behaves kind of, if you want to understand what it does on general skew adjoint things, it really behaves just like the cross product that you've seen in vector analysis. And remember, remember that this guy is going to change sign if you interchange A and B in the same way that this changes sign. But this relation between, so in this particular case, it's going to turn out that the Lie algebra of SU2 really is really just the usual three-dimensional space with this where you've taken the cross product, where you put a product on the space and it's the cross product. We'll see a lot more about that next week. Okay, let me see the other things I wanted to. Okay, and then just maybe one last comment about this is that okay, here's the last. And here I think maybe I'll go back and show you a picture for the book. Is that the so the xj give a basis for the tangent space is to SU2 at the identity. And let me go back to this. Let me go back to the screen and where are we? Okay, so I guess maybe that's all I really want to say about SU2 and about the n is equal to 2 case. So are there any questions about it? I see that, yeah. I should be keeping track of what's going on in your chat, but people seem to be helping each other there. But is there was there any question from the chat that people hadn't figured out? You have a question? No? Okay. So let me then go on to the second part. The second part of this. So that's the second part of what I wanted to do today, was to really tell you about just to kind of go through at lightning. So this is going to be the world's fastest linear algebra course. You're going to see. So I think what I'm going to do is just really go through these. I mean, I've written, I don't know, there's about 10 pages or so of notes on linear algebra. And I'm kind of hoping this is everything I've said is something people have seen before. But I'm going to just go through it and try to say, to pick out a few places where there's something that sometimes in linear algebra class doesn't really get emphasized very much or doesn't get explained very well, and that we're going to make heavy use of. So let me do that. But so let's just say, so here's and again, so one of the main uses of all this is going to be, well, anyway, let me just go through this. So linear algebra is really all about vector spaces. So you've always got so we're going to have a vector space B, vector space. And if you know about the general story, vector spaces are vector spaces over a field. There are things you can take linear combinations with respect to some field, but we're actually interested in we're always going to have two kinds of vector spaces. So over R, real number, or C. So our vector spaces are always going to be real or complex. Means you're allowed to take real linear combinations of things and you're still in the vector space, or you're allowed to take complex linear combinations in the vector space. But we have to be, and we're going to be more careful than usual about which one we're talking about, because they're interesting. Sometimes we're going to have to move from one to the other in order to do something, and some interesting and confusing things can happen if you don't keep track of whether you're talking about a real vector space or a complex vector space. And so, for instance, these tangent spaces of Lie groups that I've been talking about in the Lie algebras I'm going to talk about next time are real vector spaces, whereas the state space And the representation spaces that we're acting on are going to be complex vector spaces.
Okay. I have a question, Professor.
Yeah.
I'm thinking about the last comment or the last part of our discussion. So you said xj give a basis for tangent space to SU2 and identity, and I'm just thinking about the fact that so SU2 is the group of rotation matrices in R2, or at least it can be thought of that.
No, well, no, it's not. So you're thinking of SO2.
Oh, okay, yeah.
Yeah. So here, So it's SO. Remember, so here, if you take anyway, yeah. So rotate. If you're rotating in 2 dimensions, that's SO2, and that's actually the same thing as U1. And I'll say a bit about that again. But then, so the problem with something like SU2 or with U2 is these are transformations acting on C2, which is a 4 real dimensional space. So it's very hard to kind of visualize them. And we're going to, we'll say a lot about them and develop various kind of facts about them and ways of working with it. But they're I mean, SU2 or U2 are not at all intuitive objects, unlike SO2. If you're, in two real dimensions is easy. 2 complex dimensions is much trickier to think about. Okay.
Professor, is SU2 rotations in 3-dimensional space? Because we need 3 parameters to characterize this group, right?
Okay. Well, this is something. Yeah. Again, we'll get to in a week or so. There's a very subtle relationship between SU2 and these unitary transformations in 2 complex dimensions, and SO3, which are the rotations in 3 real dimensions. So these are related things in a very subtle way, but that's going to take a whole lecture. I can't. Okay, we'll talk about that.
So you need to map your S3 into the tangent space of S2 when you relate the 2 spaces. Relate S2 with the rotations in R3.
If I want to relate, so SU2 is just, you can think of it as just as a space. It's just the 3-dimensional sphere in R4.
But the 3-dimensional sphere has a mapping to the tangent space of the 2-dimensional sphere.
There isn't any. There are lots of maps from.
I mean, the Hopf map is a map from S3.
Okay, yeah, but you're getting into very you can't, you can work in higher dimensions by mapping to lower dimensions, but the problem is there are lots of ways of doing that, and then everything depends upon the mapping, and so I don't want to. I really want to stick to just some very simple things today. Let's not get to, and we will get to things to all the subtleties of this geometry later, but I think I better today. Yeah, what I wanted to do was a combination of very, very concrete things, just about 2x2 matrices, and then and then just kind of general technology about n-by-n matrices, which you've seen before. Those are the things I want to kind of get to today, and then once we've got that technology down, and then I can try and we can talk about some of the more subtle things. Okay. Yeah. So the slightly tricky things that I wanted to say about linear algebra is that one thing that we're going to do is we're going to keep track of the. I want to kind of carefully keep track of when you have a vector space and then when it's dual space. Because one thing that's going to be continually confusing in this subject is that we want to move. Are we talking about a vector space or its dual space? And so remember, let's see the so the dual vector space. So is what I'll always call this V star. If somebody gives you a vector space, the dual space is, so this is going to be a set of linear maps from V to either the real numbers or the complex numbers, depending upon which it is. Okay. So this is the abstract way of thinking about it. And then the point is that then what we're interested in is you have linear transformation So the other main topic that you talk about in linear algebra, besides vector spaces, is linear transformations on vector spaces. And so if you have a given a linear transformation, L acting on V, and so I'm trying to think about this abstractly. It's just a linear transformation is just something that takes, linear combinations to linear combinations in the right way. And once you choose a basis on here and write everything out with respect to a basis, then these become matrices. So you can concretely think about them as matrices with respect to basis, or you can abstractly think about them in a basis-independent way. And I want to be able to do both. And this is what you need linear algebra for. Okay, and then the point is, so if somebody gives you linear transformations on V, that you have there's a corresponding linear transformation on the dual space of transformation. And this is just what I'll call the transpose. And you call it the transpose because if you write everything with respect to matrices, taking this linear transformation is going to be given by the transpose matrix. But if you don't, but you can on V star, and it's given by. Well, let's see if you want to take it is that L? Actually, I think I wrote this. Well, let me write it that way. Given by LT. So LT applied to so if L is if L is a linear map on here, or something in the dual space, then LT of L is a thing that if you apply it to, you feed it a vector. This is going to be a new. So you have L going to LT L, which is also. The point is that there's the linear transformation from elements in here to elements in here is given by you take a linear map here, and you get a new linear map, which is just given by taking L of L. So this is all just kind of abstract nonsense definition, but and if you look at what this means very concretely in terms of matrices, it's really things are just getting transposed. You're taking row things to column things and vice versa. But I do want to sometimes use this abstract point of view. And the importance of the let's see what I want to. Okay, so one way that I'm going to want to use this is let's relate this to our representation theory. So remember, so if you think of representation theory as just I found a bunch of, for each group element, I found a linear transformation on a vector space, and that they all behave in a nice way as a homomorphism. Well, let me.
Quick question, Professor?
Yeah.
So let's say, imagine we're in a R2, and then so like little l would be a row vector then, right? And capital L would be a matrix. And so like,
yeah,
I mean, we're like this statement that you have that you just kind of erase the right side of, but it's still partly there. Like, that's just saying if you take, I mean, you can just switch a matrix and a row vector, switch the order of them by transposing the matrix.
Yeah, so this corresponds to when you're writing dual elements as row vectors, then you're using the fact that then L of V. So if you write vectors as things like this, and you write dual vectors as things like this, L, and then the point of this notation, one point of this notation is then that L, this guy evaluated on this guy, is the dot product. Okay. And anyway, he then becomes just the matrix multiplication of this. But I'm sorry, I'm afraid that this is really the level of technology I don't want to kind of review, partly because it's actually very confusing. and if I try and just kind of jump into it and start explaining the and start trying to get into the technology of the linear algebra class without any kind of careful buildup of exactly how I'm setting up the formalism, I don't think I'm gonna make anything less confusing. I'm just gonna make it more confusing. So that's right. I just want to, so I don't actually want to get right now, I've tried to write out some of the details in the notes for how to go back and forth to the, to writing things in terms of a basis and in terms of coordinates with respect to a basis, and then what happens. But I don't want to try and go through here, because it gets, you have to take very careful about which direction you're going, and it's just going to get more confusing. But so let me take a look at what's in the detailed thing I wrote in the notes. If that doesn't make sense, let me know. I mean, that's quite possible also. But all right now, I just want to tell you a few general things that come out of here, but that are going to get used in the course, because they tell you something about. I want to say some things pull some things out of linear algebra, which are useful, which tell you something new about representation theory, because we're going to see them and need to use them repeatedly. Okay. And so the thing that I wanted to get here, I wanted to take out of this was really just this. Is that, given it, so if you're given a representation on V, you get, so let's call it pi. Let's call it pi V. You get the, I forget what notation I want to use for it. You get a dual, you get a representation, so right now I'm keeping the vector space and its dual kind of separate. It's two different spaces, but I'm going to get a representation. And I don't know what notation I wanted to use on it, but notation on V star. And this is going to be called the dual representation. You use it by taking the matrices, or by taking the operators. Okay. So we started. So here we had these guys pi of g. We had these linear operators, one for each group element. But now what we do, if we take pi of g, so take pi of g and take pi of g, take the inverse of this. Take the inverse of this, and then take the transpose. Okay. And this is going to be a map. So you had these linear operators. You started with which took v to v. Well, you take and they're invertible. You take the inverse one. Take the inverse, but then you take the transpose, and the transpose is what acts on the dual space. So this is the thing. This is a linear operator that takes the dual space to the dual space. Okay. And so, anyway, so this is just kind of an abstract fact which we're going to see and have to use at various points. Is that if we're doing representation theory, and somebody's given us a representation on a vector space, well, there is going to be a there's a corresponding representation on the dual space, but and it's given abstractly by first taking the inverse of the ones you started with, and then taking this abstract transpose. In terms of matrices, then it really is just the fact that you are just taking the inverse matrix and the transpose matrix if you're working with matrices. And the point is, remember that you need this to get, yeah. So the homomorphism property. Yeah. So this satisfies. I guess this satisfies the homomorphism property that pi of G1 inverse T pi of G2 inverse T is pi of G1 G2 inverse T. Okay. So that the kind of funny thing you have to do where you have to take the inverse and you have to take the transpose, that that causes the you can show if you play with this for a minute, and I think I do this in the notes, you can see that if the pi's satisfy the homomorphism property, then this also has to be true. But this is just a little bit of abstract nonsense, but which I wanted to say because we're gonna have to use it in various points. Okay, and then the other kind of general thing to say, it's kind of crucial, is that we're really, like often in mathematics, you know, you can get a much more concrete calculation by going and choosing a basis, but you've got but what you're actually interested in are things that are aspects of the situation that are independent of the choice of basis. So so a fact again from linear algebra is that if you go, so in linear algebra you have a change of basis formula. This corresponds to if you change the basis with respect to which you're doing calculations, then your linear map or your linear map then gets conjugated by some transformation that the transformation that relates the two bases. So it's going to be L goes to A inverse. I'll write it this way. So this is where I'm not really telling you any details of this. This is just something you should have seen in linear algebra. That if you've got a linear transformation and you want to see what happens with linear transformation when you do, you know, some kind of invertible transformation, which changes your basis or changes how you're describing the vectors on your vector space, then this is what happened. Then this guy changes. These guys change by conjugation. And so the kind of the information about a linear transformation that's independent of the basis is the information that doesn't change when you conjugate the matrix. And we'll see a lot of that again starting next time. Okay, then the next thing is, so everything I've told you about so far doesn't depend upon a choice of inner product. These are just vector spaces where you don't necessarily have a notion of distance or angle. They're just vector spaces. And vector space V and the vector space V dual in general are two completely different things unless you have an inner product. So let's go back to inner products. Inner product. And so in the real case, so the real case, an inner product is really just a map. I forget what I wanted to. So I think well, anyway, let me not even try and go back through the whole definition or whatever. But you've got something. I'll write it this way. It's something that you put two vectors. You put two vectors in here, and you get a number. It's the dot product of the vectors. It's the inner product of the. It's the inner product. And in the complex case, I'll often write it with these brackets. Okay. And now the crucial. So here it's called a. We use a specific inner product which is called the Hermitian. It's called the Hermitian case. And the point is that you have to, in order to get this, well, if you try and do the same thing over the complex numbers you did over the real numbers, it turns out you have to make a choice. Here you're real linear on both sides. This is linear on whatever you put here, linear on whatever you put here. Here you have to make it linear on one side, anti-linear on the other side. So what you can do is so you have to make a choice, and we're gonna make the choice that it's anti-linear here on the left side. Okay. So whatever you put in here, if you multiply it by a complex number, your answer is going to be multiplied by the conjugate complex number, not by the complex number itself. And so that's a choice of convention. And I think I said this before, that physicists pretty much always use this convention. Mathematicians sometimes use the other side about half the time. Okay, so that's inner product. But the point about an inner product is that these provide, so these give an isomorphism of V. So in a world where there are no inner products, which is sometimes we're going to see this, we're going to work with cases where we're thinking about a linear space where there really isn't an interesting inner product, then V and V dual are just two different things. But if you do have an inner product, you can use it to relate these things, and you relate it just by L. So V, if your V is in V, the isomorphism maps this to LV, where LB of W is V W. Okay. Or either round or angular brackets, depending upon whether you're real or complex. Okay. So this is just
a question.
Yeah.
In the definition of the nodes, you say that the inner product is non-degenerate. I'm not sure what you mean by that.
Okay. So I mean, you have to. Well, so in the simplest case, I guess the simplest case of inner products, what I want is the case where you have where you have V is rated as V squared. It's the norm squared of V, and this is equal to so non-degenerate means that this is equal to 0 only if. Well, I don't really mean it. Well, let me actually just say this. I want for now I want to stick to the case. This is 0 only if V is equal. So if V is equal to 0, okay. So I'm again, I don't want to get into the general story, but if you want to. You have to put some kind of condition on the inner products besides linearity on both sides in order to make for this to be an isomorphism, and you have to put some other condition of positivity if you want this to be true. But for now, just for what I'm talking about now, I just want to think about inner products that are what I would call both non-degenerate and positive. Okay, I don't want to put other things.
I guess. I guess this is also a condition we need to prove the mapping that you write on the board is an isomorphism.
Right. Yeah.
Okay.
Well, it's a little bit more confusing than that because you need let me just say that non-degeneracy is whatever I need for this to be an isomorphism. Positivity is the extra condition of positivity is if this is true. It is possible to have non-degenerate inner products which aren't positive, but I really don't want to go there today. Okay.
Wait, thank you.
Okay, let's see how much time I got for more of this. Okay, now, so once you have an inner product, then you also have a notion of the adjoint of a linear operator. And so that's what we're going to next. So if how did I want to? So you can define so abstractly the adjoint of a linear operator is the so the adjoint of a linear operator here, L such that V goes to V is the operator satisfying I'll call it L adjoint in that sense. Then that L, if you act on it here, on two vectors here, it's the same thing if you V L adjoint. Okay. So just the takeaways from this are more that this is so again this is a coordinate independent, doesn't depend upon a choice of basis description of the adjoint. If you then translate this into what happens when you've chosen a basis and your linear operators are matrices, then the adjoint, then in terms of matrices, what you do is you show that this condition corresponds to taking the transpose and the complex conjugate. Okay, and so in terms of matrices, you say that the adjoint is that you take the matrix, you take the transpose conjugate. Well, more abstractly, the reason that's an interesting operation to do is that operation is kind of keyed to the inner product in a nice way, and that this is true. So this is the abstract version of what it means by adjointness. Okay, now the other so when you're given an inner product, you have this notion of adjoint. You also have this notion of you also have well, let me first do it for the real case. Well, yeah. No, so you also have a condition. Let me just say the condition first. The condition that L preserves the inner product. So in other words, LV, LW is VW. Okay. So the idea is that once somebody gives you an inner product, what you can do is instead of looking at all linear transformations on that vector space, all possible linear maps, you can look at those linear maps which don't change they don't change lengths and angles. And in the real case, these are called orthogonal transformations. Okay, and starting to, this is where starting to run out of time here, but these then they then satisfy. Okay, so remember I said that the adjoint was what you got by taking the in terms of matrices, it turned out to be what you get by taking the transpose and the conjugate. Well, in the real case, you don't have the conjugate to worry about, so you just have the transpose. And so orthogonal transformations, if you haven't done this before, you should go through the exercise to check that these satisfy the condition at L. They're going to do this when you have that the L transpose is equal to the identity, or that L transpose is equal to the inverse. So this is the condition for what's called an orthogonal matrix or an orthogonal linear transformation. But it really, if you look into why this is an interesting condition, it's an interesting condition because this is true for the inner product. Okay, for the standard product. And so you can ask about what and then that this you can check to see what the determinant this implies. So this condition in particular implies that the determinant of L transpose is 1, but this is also equal to the determinant of L times the determinant of L transpose. But if you take the determinant of the transpose, it's the same as the determinant of the original thing. So it's the determinant of L squared. Okay. So the bottom line here is that orthogonal matrices are the things that satisfy.
Wait a minute. How do you define the determinant in abstract matrix?
Okay. Yeah. Yeah. Okay. So
especially when the V is infinitely dimensional.
Okay. First of all, everything is finite dimensional, but
okay.
Everything's fine. But the determinant, so if the determinant is something which typically, you're taught about in terms of some complicated formula involving matrices. There is a more abstract version of it, which but I think I better not try to tell you that. It's the determinant of a linear transformation is the coefficient by which the top dimensional form changes when you do a linear transformation. Anyway, I better not try and do that. But I'm just saying something very simple that these are gadgets which you can think of in terms of matrices, or you can think of more abstractly. Then if you use the matrix, you get a determinant, and the determinant squared is equal to 1. So this implies that the determinant is equal to plus or minus 1. Okay. So just the thing to keep track about orthogonal matrices is, so here's some notation. So let's say O of n is the orthogonal matrices. And let me just think of them in terms of matrices, but you can think of them in terms of transformation. And these, but the point is that these kind of break up into, if you think about these as a space, there's two spaces. There's the ones with determinant 1, and there's the ones with determinant -1. And they're the ones which kind of do a kind of a rotation of your space, and they're the ones that do a rotation and a mirror transformation. And so inside here, you've got the ones which have, these are called the special. So these are the ones with determinant is equal to +1. But if you want to think about this guy is this guy plus another component, which is kind of essentially the same thing, but with this mirror rotation going on. So but orthogonal matrices. So we had, for n is equal to 2, SO2 was just the rotations in the plane, and so it was isomorphic to this U1. It's all things in the form cosine theta minus sine theta, cosine theta. O2 is going to be things like this, times a reflection in the plane. Okay. So that's the orthogonal story. Then just quickly, I think I better just take a few minutes to tell you what the unitary story is. And also one of the, there's a lot more details in the notes. One of your problem sets also, I think, ask you to do to work out some more of these facts about unitary groups. But let me just tell you the basic fact that here you have so unitary groups. Okay. So this the same kind of condition that again you have something you have a linear transformation times the adjoint transformation is the identity. This corresponds to LV LW. So you can ask what's the condition on linear transformations on Cn so that the linear transformations preserve the standard Hermitian inner product, and that turns out to be this condition. And you can also think of it as that L dagger, and this is the dagger, is L inverse. Okay. So this is the unitarity condition, and we saw it for these SU2 case, for this SU2 case. But now, if you take the again the same argument that I just erased here tells you that the determinant of L, well, you end up with the determinant of L times the determinant of L dagger is equal to 1. That this is part of the unitarity condition. But then now the determinant of if you do the transpose doesn't change anything, but taking the conjugate changes this. So this is the determinant of L times the determinant of L conjugated is 1. So the determinant of L is a complex number that satisfies that. Okay. So a complex numbers with length squared is equal to 1. Again, it's just going to be given on some point on the unit circle, and these are going to correspond to anyway. So one aspect if somebody hands you a unitary matrix is it's an n by n matrix that satisfies this condition, and it has a determinant which is either the I theta for some theta. Okay. But now, so let's just rewrite this here, and then so then U of n and is unitary n by n matrices. And then SU of n is a subgroup of determinant is equal to 1. Okay, but now the determinant 1 condition is picks out one of an infinite number of possibilities. It picks out this point here on the sphere. Okay, so the whatever dimension the space of SUN is, U of n is going to be one more dimension. U of n in some sense has kind of an extra circle in it besides all the dimensions of SUN. Okay, so I think I better stop here. It's getting to be time now, and I definitely, depending on how much linear algebra you've seen before, I definitely try looking through these notes. And if you have things that are confused about it, you can ask me about it. Or we can talk a little bit about it next time. Or if you want to stay after class, I'll be happy to. And again, in a few minutes, I'll start up the office hour Zoom session. But I have to kind of. I mean, if you haven't seen much linear algebra before, apologies for kind of subjecting you to kind of a 30-minute linear algebra class, which is not so may not be so useful. But hopefully you've seen much of what's in these notes before, and I was trying to pick out the things that people are kind of least likely to have seen, and that we're going to actually use a bunch in this as we go on further. Okay. Okay. So any last questions for today? No. Okay, well, if there are no questions, I'll shut this down, and people who want to have time to stay along and talk some more, come back to the other Zoom session. Okay.
Thank you, Professor.
Bye for now.
Thank you. Bye-bye.
Bye.
Thank you.
Bye.